Good. So, hello everyone. I am Faiza Khorram from IMT Atlantique of Nantes in France, and I'm going to present our paper that is titled From Coverage Computation to Fault Localization, a generic framework for domain-specific languages. Our paper is indeed in the context of executable domain-specific languages, or xDSL. These are DSLs that provide an execution semantics and are mainly used for describing behavioral models. We call a model behavioral when it represents dynamic aspect of a system. And as an example, we are going to use an example xDSL in this presentation that is used for modeling Arduino boards and their behavior. I don't know if you're familiar with Arduino or not, but Arduino is a kind of company that provides some boards that these boards have different pins, and each of these pins can be connected to different modules such as LED, infrared sensor, and button. And the Arduino company itself provides an integrated development environment to define the behavior of the Arduino board using C or C++. But with our executable DSL, we are actually able to define the model, both the physical part and the logic, using the concepts very easier than C or C++ somehow. So as you can see on the right side, on the top, you see the board and some modules that I consider for my model. And what I want to model is a kind of basic intrusion alarm system. So the behavior of this Arduino board is shown on the bottom. As you can see, what I express here is that if the button is pressed, so equals to 1 is actually represented as being pressed, the LED should turn on. And then if the sensor detected something, the alarm should turn on, then wait for 1000 milliseconds, then it should turn off and wait again. And at the end, when the sensor doesn't detect anything, the alarm should turn off. And then when the button is released, the LED turns off. But here we intentionally have a defect because a part of the contribution of this paper is about fault localization, and we will see how the approach can help to find this fault of the model. So, as I said, we are working in the context of xDSLs. And in the definition of an xDSL, one part is the abstract syntax, of course, that defines the domain concepts and the relationship between the concepts. And we consider that the abstract syntax is defined using an equal meta model, which is one of the most popular ways of defining it. And for example, on the right side, you're watching the equal meta model of Arduino DSL. The root element is a project which can have several boards. Each board actually represents a physical Arduino board. So a board can have several pins, each connected to a module, such as an LED, a sensor, and so on. And to define the behavior of the board, we have a concept of a sketch in our DSL that for each sketch, you can define a block of instructions, such as a module assignment, a delay, or some control instructions, such as if and while. The second part of a DSL definition is its execution semantics, and we are considering only DSLs that provide execution semantics as an interpreter or an operational semantics. An operational semantics definition should define what are the possible runtime states during the model execution and how the runtime state of a model changes over time, and actually by defining some execution rules. To define the runtime states of the models for a DSL, we consider that we can define new features for the existing meta classes of the abstract syntax or even new classes. So kind of extending the equal meta model with new features, such as here that we have added a new feature for the digital pin level. And for instance, imagine that if we have a digital pin that is connected to a push button, when the level changes to 1, it means the button is pressed. And when the level is changed to 0, it means the button is released. So by changing the level, we are actually changing the runtime state of our model. But these changes is actually happening by calling the execution rules of the DSL interpreter. And the B part here shows some of the execution rules for our Arduino DSL. For instance, when the press rule can be called on the push button instances. And when it is called on one push button instance, it actually changes the level of its connected pin to 1 to actually simulate the behavior of pressing a button. And finally, the definition of an executable DSL also contains at least one behavioral interface, which defines how we can interact with a running model. And as you can see in the C part, a behavioral interface comprises several events, some accepted events that defines how we can send data to a running model, and exposed event that defines how a running model actually reacts to the external environment. And both of these events can have parameters with different types. In our previous work, we provided a generic approach that allows writing test cases for executable models. And to give you a very brief overview, a kind of test case that we can define for executable models is something similar to what you can see here on the right side. So it's a kind of something similar to a sequence diagram, but messages are exchanged between a test component and a system under test that in our example is an Arduino model. And the kind of data that is exchanged between these two components are actually instances of the events of the behavioral interface of our Arduino DSL in our example. Both the input data and the expected output can be defined by instantiating the events of the behavioral interface of the DSL. And also, our previous work provides facilities to run test cases on the models and get the verdict. So the main questions that we were asking in this paper was that, considering that we wrote some set of test cases for our models, how we can make sure that these test cases are good enough, they have a good level of quality, and how we can localize the faults when test cases fail on the model. Well, in the context of programming languages, coverage computation is a well-known technique that can answer actually both of these questions. Because with coverage computation, we can actually measure the quality of the test cases by measuring how much of a system under test is exercised by an executed test case. And at the same time, coverage is also the basis of an advanced fault localization technique that is named a spectrum-based fault localization. But when we are thinking about coverage computation for executable models, what we face in general is the diversity and heterogeneity of DSLs. DSLs are small languages for specific domains. So since there are very different domains, there are different DSLs, and there will be new DSLs in future. And because of this diversity, the existing coverage computation approaches are mainly defined for particular executable DSLs. For instance, in the literature, there is a state coverage for state machines, but they are not reusable for other DSLs. And because of this issue, for every new DSL, a new coverage computation approach should be defined from scratch, but it's very costly and error-prone and repetitive, of course. So the objective of our work was to provide a generic coverage computation approach for executable DSLs. To bring this idea of coverage computation as a generic way, what we need at the first step is to see any executable model in a generic format. And what we observed is that we can consider each executable model, for instance, here our Arduino model, as a specific kind of graph where each element of the model is actually one node of the graph, and the connections between the model elements can be considered as edges of the graph. So if we see any executable model as this specific kind of graph in a generic sense, by computing something like node coverage, we can actually compute the model element coverage. So we can have a kind of generic coverage metric that is applicable to any executable model. But how this can actually compute it based on the way that we execute models. So considering an executable model and a test case that is executed on that, we want to compute the coverage using the metric that I just described. What is actually happening in the test case execution is that once a test case needs to run the model under test, it actually performs different calls to the execution rules of the DSL that the model under test conforms to. In our example, Arduino execution rules. And every call to these rules will be captured in an execution trace, which actually refers to the elements of the model that is exercised. So it means by analyzing the generated execution trace, we can actually see which model elements are captured by the trace. That means they are actually covered by the test case. But as you can see, and there are some yellow highlighted elements. These are the elements that are not seen in the trace. But the question is that are these not traced elements not covered by the test case, or they are not traced because what we have in the execution trace, it actually depends on what kind of execution rules we have in our DSL definition. So the granularity depends on that. Before answering that question, we considered that in addition to computing coverage based on execution trace in a generic sense, we can also consider that a language engineer might want to define some DSL-specific coverage rules. In general, we consider that two families of rules could be interesting to be defined for a DSL. We named them inclusion and exclusion rule. By inclusion, the idea was that maybe from the coverage status of some object, we can infer that some other object, some other connected object is also covered. And by exclusion, what we mean was that maybe a language engineer wants to ignore some specific types of elements from coverage computation under a certain condition. To provide such flexibility to our generic approach, we proposed a meta language that allows a language engineer to define DSL-specific coverage rules. And you can see its concepts using an equal meta model on the right side. So a domain-specific coverage can be defined for a meta model and actually for different meta classes of the meta model by defining context. And for each context, we can define different kinds of rules. Right now, we consider 4 types of rules: coverage by content, which actually uses the containment relationships to define coverage rules; coverage of reference, which uses non-containment relationship between elements to define coverage rules; and ignore and conditional ignore, that you ignore elements. You will see examples in the following. So, the first step that we perform is analyzing the execution trace of the model under test to compute some initial coverage status. For example, for some of the elements of our Arduino model, you can see the initial coverage status for them. The next step is that we check whether the language engineer provides some DSL-specific coverage rules. And here on the left side, you see you're watching the concrete syntax of our meta language. Here we define a set of rules for our Arduino DSL. For example, we define a rule for module class, and we want to say we are not interested in the coverage status of module elements because they are just representative of physical elements, and we want to only consider the behavior parts of the Arduino. So after applying this rule, the coverage status of the push button element is changed to not traced because we are not anymore interested in this coverage status. But more interesting than that, we also have another rule for the if context. And what it says is that whenever an if object is covered, its referenced condition element can be considered as covered. And as you can see, the coverage status of this expression is changed to covered after applying this rule. And at the end, in the next step, the coverage status for all the other elements that do not have any coverage status so far will be changed to not covered. And finally, the values of the last columns will be considered as the coverage matrix for our model under test. So to give you an overview of the approach that we proposed, what we consider is that a language engineer provides an executable DSL that is used by a domain expert to define executable models. And this domain expert also defines some test cases for the model. And we also consider that there is a test execution engine that can run test cases on the model and produces the test execution results. and the execution traces of the model in a generic format. By considering all of these artifacts and components already existing, we added a new component to this architecture that we name it as X model coverage computation, which uses the DSL definition and reads the execution traces to compute coverage. And as you can see, we have added a new component to the DSL definition, which is of course optional. So if there is any, we use it to update the coverage. If there isn't any, we just continue with the generic coverage computation. Well, earlier I mentioned that coverage is also the basis of a spectrum-based fault localization. In this, with SPFL, actually, we have a set of formula, a set of kind of mathematical formula that computes a kind of a score for different software components. And the parameters of this formula can actually be computed using the test execution result and the test coverage. For example, here, you see a popular SPFL technique, which is named Tarantula. And the parameters of this technique can be computed using test result and test coverage, such as NCF, which is number of failed test cases that cover the element, and NCS, number of successful test cases that cover the element, and some other values. And for instance, here, the main idea of Tarantula is that the test cases the elements that are covered by more successful test cases are less likely to have faults, and the software components that are covered by more failed test cases are more likely to have the fault. So this is the main idea of Tarantula technique, and there are some other techniques in the literature. What we could achieve here is that since we bring coverage computation in a generic sense for executable models, by substituting the notion of software components with model objects, we can actually bring a SPFL for executable DSLs in a generic sense. And in that case, we can automatically produce a suspiciousness-based ranking of the model elements using the SPFL techniques. So we have added a new component to our approach that uses the test result and the coverage result and produces a suspiciousness ranking. And finally, all of these outputs will be visualized for the domain expert using a specific user interfaces. And in this slide, you can see one screenshot of our provided tool. So we also save the test coverage and the test result as XML files for later use. On the top, you see the coverage view. So as you can see, for each model element and its type, we visualize what is the coverage status of the element by each test case and also by the whole test suite. And in the last row, we show what is the coverage percentage for each test case. And on the bottom, you are watching the fault localization user interface. We are currently supporting 18 SPFL techniques in our tool. So once a user selects one of these techniques from this list, the values of these last two columns will be calculated. So the values of all of these parameters are calculated automatically based on the test result and test coverage. But these last two columns are computed based on the selected techniques. And as you can see here, for the faulty element of our Arduino model, the rank is correctly 1. So the faulty element is ranked as first, which says the domain expert that look at this element. But there are also some other elements with the same rank. That is one of the common issues with SPFL, and there are some strategies to break these ties of the elements, but it's left to our future work. To evaluate our approach, the first research question that we had is how much genericity is supported by our approach, considering the supported DSLs, but at the same time, how much customization is needed to achieve the intended coverage computation. And to answer this question, we examined our approach in a case study on 4 different DSLs: xFSM, xArduino, xPSSM, and xMiniJava. xFSM is a simple language for describing state machines that can process a string. xArduino is a DSL for that I just shown you. PSSM is an executable DSL for describing UML state machines, but in EMF. And Xmini Java is actually an interpreted and simple version of Java. And you can see that they have different sizes based on the number of e-classes of their abstract syntax. For each of these models, we have defined a set of, each of these DSLs, we have defined a set of models, in total 21 model. And we also defined a set of test cases for each of the models, and in total 297 test cases for 21 models. And actually, with our approach, we were able to define in total 25 DSL-specific coverage rules using the meta language in 151 lines of code. And using the approach, we were able to compute the coverage of all of the written test cases. In the second research question, we were interested in seeing to what extent the result of our coverage computation approach is valid. As I said, Mini Java is a simple version of Java. So it allows us to make a kind of comparison between our coverage computation with some existing coverage tool of Java. So we randomly selected a set of test cases of our Mini Java model, and we compared the coverage that is computed by our approach with the coverage of the equivalent JUnit test cases for equivalent Java programs, equivalent to our Mini Java models and test cases. And as you can see, we achieved a pretty similar result as code coverage tool. And there are only a few differences between our computation and code cover. And it's because some specific elements are considered by code cover, such as the closed bracket are considered with code cover. And finally, we also wanted to see how much our generically computed coverage are useful for fault localization to bring SPFL. And to actually measure, to actually answer this research question, we first need to have some faulty elements in the model and some faulty programs to see whether our fault localization approach is able to detect them. To generate faulty models, we used mutation analysis. As you can see, we have defined in total 184 mutation operators for each of for all of the DSLs in total. And by applying these operators on the 21 models, we have generated 1,079 mutants that are the faulty programs. And among them, for 1,069, almost 98%, at least there was one SPFL technique that ranked the faulty element of the model as first. So it shows that the coverage computation are useful for performing fault localization as well. We also submitted our artifacts for artifact evaluation. Unfortunately, we got 2 badges. And this was a joint work between IMT Atlantic and JKU University of Linz. And thank you very much for your attention. If you have any question, I would be happy to answer that.
Okay, thank you. So one quick question, please. Any question? Okay, yes. So where is someone? Oh, yeah, thank you.
Nice presentation. Test. That works. Yeah, thank you.
Yes.
I was wondering if your approach, how difficult it is to apply it on non-executable domain-specific languages.
Well, I guess with coverage, what we mean for computing coverage, we first need to run test cases. And to run test cases, we need to run models. So do you mean compile DSLs in other kinds of running the model?
Yeah,
or
for example, DSL that have a translation to a different language or something, where we might have tests in a different language, or we have a certain specification about this translation process, but not having actual concrete tests.
Yes, I see. I guess Our approach could be useful, especially the meta language, to define the DSL specific coverage rules. But if you are going to use a compiled DSL, it means all the execution facilities will be provided by some other compilers, and maybe for another language, for instance, Java or some other programming languages. And in that case, the definition of the execution trace will be different. And in our paper, we are actually considering a generic format for execution trace. And we consider that the rules are called on the elements as a generic sense. But if with compiled DSL, we should change that definition of the execution trace, and it has a direct impact on the way that we analyze the trace to see which element is covered and not. And as you said, it's also important how each model element is translated to the software components of the final executable code, and how we can trace them back to the first level to actually show the coverage in the modeling level. But we're more interested in providing all of these facilities in the modeling level. So that's why we considered interpreted DSLs.
Okay, thank you.
Okay, thank you very much. Let's thank the speaker again.
Thank you.